Welcome back to another video on probability theory. Last time we encountered the Borel-Cantelli lemma, which answered the question if some events occur infinitely often or not infinitely often. We saw there that the probability that something comes up infinitely often is either 0 or 1. So there were no other possibilities in the Borel-Cantelli lemma. And today we are going deeper into this topic. The so-called Kolmogorov's 0-1 law says that if the things that I'm observing are independent, the probability that something happens infinitely often is either 0 or 1 and nothing in between. Let's see how we can show this. So, Kolmogorov's 0-1 law. I have to start by recalling something, which we're going to need, which is a proposition what we will need here from measure theory. We briefly also recall Dynkin systems, I guess. If not, then please look it up in the course on measure theory. And what is a Dynkin system? It's a set system with a property that the whole space is in it. If two sets are in it and one is part of the other, then the set difference is in it. And if you have an increasing sequence, then the union is also in it. So it's a bit more restrictive than in a sigma algebra. In sigma algebra, you would need that the union is in it, no matter if they are part of each other or not. But there's a theorem which is important, which we need today. If you have some C which is intersection stable, then the sigma algebra generated by C is part of D. Whenever D is a Dynkin system bigger than C. So for example, you could say D is a Dynkin system generated by C, which is a Dynkin system which is bigger than C. Then the sigma algebra generated by C is smaller or equal to the Dynkin system generated by C. And how we are using this, I will show you in a moment. And it will lead to a proof of this proposition here. CI here are independent intersection stable set systems. Then it is claimed here their generated sigma algebras are also independent. So that's a powerful thing because you only have to check independence here for smaller things and then you get it for the generated sigma algebras for free. So how can one prove this? So first of all, we only need to prove independence for any finite subset of I. Let's just call it subset I1 until In subset of I. And without loss of generality, well, it should contain an element. Okay. Then we know that the probability of AI1 intersected with AIN equals the product K from 1 to N, pay AIK, whenever AIK is in GIK for all K from 1 to N. Let's call this property here star. I'm not giving you the full proof, I better give you the strategy of the proof. We, for example, fix AI2 to AIN and show that a set system which we call D, which is the set of systems AI1 in F, such that star holds is something. So what is this here? So of course CI1, so by construction CI1 is part of D. That's how this is done here, because for all AI1 in CI1 this formula here holds. But it might hold for more A's, right? For example, it's easy to see that it also then holds for the complement of AI. But more is true. You can show that this D here is intersection stable, and it's a Dünkin system. Not going into the details here, but what happens now, you have CI1 is subset of D. D is this thing here. D is an intersection stable Dünkin system, exactly as here. And we then have that sigma of CI1 is a subset of D, as in the proof here, so as in this thing from measure theory, which means whenever I use an AI1 for, here's a typo, that's not JIK, that's ZIK, sorry, for all K. So we then have, whenever we have a set from sigma of CI1, this product formula then holds, because, well, they are all of these are here elements of D, and all for all elements in D, star holds. Okay, then we have that we can exchange CI1 by the sigma algebra generated by CI1, and then we do it for the second, for the third, and so on until the end. And then we are done, because then we have shown that we can exchange CIK with the sigma algebra of CIK for all K from 1 to N. Okay, and that's sometimes the case. It's a proof strategy. You say, well, I have some set system, and you prove it's an intersection stable Dünkin system. And then you can rely on this result, and then you have it for the sigma algebra. Okay, that was important. And there is a very easy corollary, which is sometimes proved also in basic probability lecture, but there it's more done by foot, I would say. And here it's rather direct. So if you have that sets here are independent, then the family of random variables 1AI is also independent. In order to prove this, okay, and what does it mean at all? 1AI. So what is the sigma algebra of 1AI? That's AI itself, but it's also the complement, and it's also the empty set, and it's also the full space omega. Because the pre-images of this function here, the pre-image of 1 is AI, the pre-image of 0 is the complement, and well, empty set and whole space you need anyway. So what this says here, if I can use the AIs, I can also exchange the AIs by their complements or empty sets or the whole thing. And how do we do this? So we are using the other bit. We take Well, Ci is the set which only contains AI. That's clearly intersection stable because there's only one set in it. It generates sigma of Ci equals sigma von 1 AI. And now we have it because that theorem here told us we have independent intersection stable set systems. Then we have that the sigma of Ci's are also independent, and they're the same as what is claimed here. Okay, that was easy. Another thing which sounds easy, and actually it is, because we have this powerful lemma from the first slide. So, well, it's like this here. So this here is our set I, and let's assume Fi's are independent. So here I have all my Fi's in it. So every single point is one Fi. And I want to group them, for example, into these 4 parts here. And I would like to say, well, when I only use, for example, here, the yellow color, purple, I don't know, bluish, so all of these here, and maybe some green thing here. Then I have a family of only 4 things, but they should still also be independent. So the yellow from the rest and so on. So grouping is the keyword here. And that works as the corollary tells us. I have this large set of all these singles here. I have a partition, as it's called, of I. For example, K has 4 elements in our example here. The union of all this is I. Then the sigma algebras generated by all the yellow and so on, that's also independent. Oh, yes, so proof. Again, we use this result. We have to define some CKs, and then we will have that the sigma algebra generated by the CKs is also independent. So what is CK? That's an intersection of AIs for I element in some JK, where JK is a finite subset of IK, and AI is in Fi. Okay, so I'm doing the intersection for any finite subset on, for example, the yellow thing here. So this here is intersection stable. And what is also true, sigma of CK is sigma of Fi, I in IK, for all K. Anything about it? So this thing here generates the sigma algebra, sigma Fi, I in IK. And now we're done, because this result here tells us that then these CKs here are also independent. The sigma algebra generated by the CK is also independent, and that's exactly what is claimed here. Okay, that was grouping. We will need that also. And we now have another sigma algebra, the terminal sigma algebra. And remember the lim sup of sets from the last video in the Borel-Cantelli lemma. This is an element of this thing here. In general, so what's the terminal sigma algebra? sigma algebra of all the terminal events. Okay, the Fn's are sigma algebras. The union is a sigma algebra. No, the union is not a sigma algebra, but the sigma algebra generated by the union is a sigma algebra. The intersection of sigma algebras is a sigma algebra. So this here is a sigma algebra. Okay, what does it contain? The union here contains events which depend on all Fm's m bigger than n. And must do so by this intersection here for all n. So that here are events which only depend on the tail of the Fm's. So 1, 2, 3, 4, 5, 6, and so on. F1, F2, F3, and so on. So in this sigma algebra are events which only depend on the very tail here, what I cannot write here down because it's infinitely long. So, for example, the event that when you have a coin toss, you have infinitely many heads, or the random, or no, the event, let's just say the event. So this is a set which is element of this sigma algebra because it does not depend on any finite number of experiments. It only depends on the whole tail, no matter where you start, but on the whole tail of the sigma algebra here. So in the term of sigma algebra, you only have things which depend on the tail, which cannot be decided if they occur or not after any finite time. That's one thing. And the second thing is F tilde is called trivial or p-trivial if it only contains elements which have probability 0 and 1. Okay. And let's first look at these trivial sigma algebras because there's a nice lemma. Sigma algebra is p-trivial if and only if it's independent of itself, which sounds a bit weird to be independent of itself, but there's a clear definition. Sigma algebra, comma itself is independent means that, well, the product formula holds, as in independence is usually the case. And the second thing is, if something is measurable with respect to a p-trivial sigma algebra, it's almost surely constant. And I would have to say p almost surely here, because also p-trivial. The proof is not hard. For the first thing, from left to right, if a sigma algebra is p-trivial, it's independent of itself. So pick two elements of the sigma algebra. We know it's trivial, and P of A intersect with B. This is, well, can only be 0 and 1. And when is it 1? If both A and B have probability 1 and 0 otherwise. So I can write it like P of A, minimum P of B. But I can also say that that's P of A times P of B, because only if both probabilities are 1, this here is 1 and this here is 1. And that means F tilde is independent of itself, because I chose A and B arbitrarily. From right to left, F is independent of itself. I have to show it's p-trivial, and p-trivial means whenever I pick an A, its probability is either 0 or 1. And the trick is that I can write that P of A equals P of A intersect with itself, of course, But I know that it's independent of itself, which means that that's P of A times P of A. Well, and P of A equals the square of P in A of A means that only works if P of A is in 0 and 1. That's what I wanted to show. Then the second thing. If some random variable is measurable with respect to a p-trivial sigma algebra, it's constant, p almost surely. Let's define C as the supremum over all x, p of x smaller than x equals 0. Which means if I take anything larger than x, then this here is no longer 0. But if it's no longer 0 and x is measurable with respect to a p-trivial sigma algebra, it must be 1. That's the point. So p of x smaller than c plus epsilon. This is 1 for all epsilon. So it's also 1 if I take the limit epsilon goes down to 0. On the other hand, if I have x smaller than c minus epsilon, well, by definition, c minus epsilon, well, the probability is 0 here, so I can subtract it. But by continuity of the measures, all which remains here, the probability here x equals c. And that means x is constant, almost surely. Okay, and now we come to the main theorem from today, which is Kolmogorov's 0-1 law, which states if you have independent sigma algebras, then the terminal sigma algebra generated by them is p-trivial. And the proof is not hard, but it's a bit tricky. Let's say Tn is the sigma algebra over the union of the FMs, m bigger or equal to n. And recall that the terminal sigma algebra is the intersection of all these here. First, F1, if I have F1 to Fn, and let me be here very precise, m bigger than n, because otherwise it doesn't work here, and Tn is independent, I claim. Why is that the case? So the Fn's are independent, and I'm just grouping everything which comes behind n to one sigma algebra, and we had this grouping lemma here, which means, well, these are also independent. So, okay, they're independent for all n. We also have that F1 to Fn and T is independent. Why is that? Because T is the intersection of all these Tn's here. So T is smaller than Tn. So that must also be independent because this is just smaller than this here. That works for all n. This means that, okay, the T here, F1, F2, and the whole sequence are independent. Why is that? Because when you want to check if this here is independent, you only choose finitely many sets from the whole sequence. This breaks down eventually. So there's the largest one. And for this largest one, we already showed that T, Fn1 to Fn are independent. So the product formula holds. then, well, grouping again. I'm grouping the whole rest here. What's the whole rest here? So this is T0 as written down here. Independent. And again, wrong direction. T is a subset of T0, which then means that T and T is independent. So T is independent of itself, which means that T must be p-trivial. And we are done. And now I have to be more precise. No, I don't have to be more precise. Of course, I was just struggling a bit because where did I use independence? But I used independence right from the start because I said that these here are independent. Otherwise, it wouldn't have worked at all. Okay, and that's it for today. So we learned that elements in a terminal sigma algebra, which is generated by independent sigma algebras, is trivial. So only contains sets which have probability 0 and 1. Great. So we're done with this and hope to see you next time. Bye.